So this is in the notes. I told you I would make a video on how to solve this equation. Solve for that final temperature equation. This is going to be me working through that problem in its entirety to include that solving. The main thing is this, what they call the calorimetry statement, which is that the heat gained by one is the heat lost by the other one. So if I have two substances, A and B, A is going to gain the heat that B lost. So for this example, they're talking about coffee in a cup. So if I start with just that statement of calorimetry, so I've got the heat lost by the coffee is going to equal the heat gained by the cup. And remember, heat always flows from hot to cold. So the coffee is hot to start, and then the heat's going to flow from the hot coffee to the cold cup. But if we just, this really just takes on really just an algebra problem at this point in time. So we're going to start with MCAT for both of them. I will not use, so let's just put it in blue. So CO, the specific heat of coffee times that temperature change. Okay. Let me try to keep everything consistent. All right, so I've got the coffee and the temperature change for the coffee, and that's going to equal the cup's heat. So we're going to have the mass of the cup, and I don't know why I put in this Q here. That should just be an MC delta T. So I got the mass of the cup times the specific heat of the cup times the cup's change in temperature. But what happens is the final temperature in both of these is going to be equal. So if I just do MC TF minus TI, right, for both sides, okay, let me go back and put a little CO, a little CU, right, CU, CO, just so we can keep things different. But you can see what happens here if I want to bring in that negative sign. This becomes mass of the coffee, C of the coffee, and then what happens is these end up flip-flopping, which will make the solving a little bit easier. You always want to try to take care of that negative sign as soon as you can. These over here will remain the same. And now you could just see it just becomes an algebra problem of distribution and then solving for TF. So if I kind of distribute in the M times CO, okay, I'm going to end up with something that looks like this. So I do the same thing with the cup. And I apologize for not writing all the subscripts on some of these. So this is the coffee. It's a little easier when you just see A's and B's. I could have just simply just did A and B. Right, so now I'm going to add this over to here, and I'm going to add this over to here to get my TIs and my TFs on the same side. The thing is, though, the TIs are different, but the TF will be the same. That's when thermal equilibrium happens. So we got mass of the coffee, cup of the specific heat of the coffee times the initial temperature of the coffee plus the mass of the cup times the specific heat of the cup times the initial temperature of the cup. Now I'm going to kind of combine some stuff here. So TF, so this is going to, if I pull it out, because that's ultimately what we're looking for. And I'm running out of space over here. Okay. So then I just, basically I've got this whole thing. We're going to divide by mass of the cup, the C of the cup, plus the mass of the coffee, C of the coffee. And what I'm using always just want to try to go to an O. And so we just take that whole thing and we just divide it by over there to the other side. Okay, cancel here, cancel there. And so there's our final equation of what I told you I would give you. So TF equals, and I'll write it just in general form, MACATIA plus MBCB TBI or TIB over MACA plus MBCB. Now, this is not given to you on an equation sheet, but I would try to memorize that or somehow memorize it with your calculator, because there probably will be a question like this on the test, or at least in the homework. So now I can plug in all my information, right? So I've got the coffee, 0.350 times the specific heat, 8.9 times 348. Now you do have to convert these temperatures to Kelvin because these are absolute temperatures. They're not specific, or they're not temperature changes anymore. So make sure you convert. Okay, we talked about that before we left for break, that with these thermodynamic type questions, make sure that we are in Kelvin, especially if it's an absolute temperature, meaning just a T, or just, if it's just a T. And that's because the conversion between Kelvin and Celsius is an addition problem or a subtraction problem, not a multiplication problem. So you go through, plug that onto the calculator, you get 346 Kelvin, but they may ask you what is it in Celsius. So that would be 73 degrees Celsius. So here is your answer. Okay, so thermal equilibrium would happen at 346 Kelvin or 73 degrees Celsius.